Okay, let's begin. So I have your tests. I'll give those back at the end. Don't want you guys distracted. We will just pick up where we left off, which is figuring out how to deal with higher order differential equations computationally. And so last time we saw that if you have like n plus a n minus 1 to the n minus 1 plus a n minus 2 y to the n minus 2 plus dot a0 y equals infinity, where the ai are constants. Find the homogeneous solution. We assume our y is once again e to the rt, and we obtain a characteristic polynomial, namely r to the n plus a n minus 1 r to the n minus 1 plus a is equal to 0. And to be able to find the roots, in order to find our y sub h, which is where we left off, and we looked at a few techniques. What order did we go into? Using lower degrees check. We looked at special factorings. Check, that's like difference of squares, sums and difference of cubes, etc. Factor by grouping. We also looked at using the binomial expansions. Check. And so now we move on to another very common situation. Namely, long division. So let us do an example. Or maybe I should tell you about some things first. There is something called the factor theorem. This basically says k of x is a polynomial if p of c equals 0, then the expression x minus c is a factor of p. As long as we can find numbers that when we plug into our polynomial the result is 0, turns out we can actually factor out an expression x minus c every such time. And there's a remainder theorem that says that the remainder when dividing by x minus c is going to be given by p of c, but I don't think you need to know that. There's another important theorem called the rational roots theorem. Another thing you want to know preliminarily, it says the following. Suppose p of x is equal to a n x to the n plus a n minus 1 x to the n minus 1 plus dot 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 a1 x plus a0, where your a n is not equal to 0. and the AI are integers. So they can be integers or rational. If they're fractions, you can just multiply the polynomial by the LCD once you set it equal to 0. Then there's a theorem that says if p of x has rational roots, it does not have to have rational roots. If it has rational roots, we actually know what they need to look like. Rational, just the root word is ratio. It doesn't mean like the roots are very rational and not. Very logical. It's a very reasonable root. No, it means
rational numbers are kind of rational compared to irrational numbers.
Why would you say that?
Because irrational numbers don't make sense. Tell me one irrational number using digits.
In what sense don't they make any sense?
Well,
so here's
put your finger on it.
How would you go about defining what's something that's normal or usual or typical? Like if you were to say, you know what, that dude is weird. Like, what are you basing that on?
Counting.
Kind of like, yeah, like the norm, right? Like he's very weird compared to most people. How many rationals versus irrationals are there?
Well, it's bigger infinity.
The rationals are the strange dudes. They're the guys that like, you can literally throw all of them away and the real numbers wouldn't miss them like literally at all. Like it's not going to make a difference in the size. They don't mean anything. Like throw away all the rationals, I don't care. The real numbers still have the same size. They're not the super interesting ones, but they're the ones that we can do within 391. So let's actually do that. Then I heard there was a story that Pythagoras either killed someone or had him killed because he posited the existence of radical 2. And he was like all about, no, the integers are the best numbers. You can't have a radical 2. What do you mean? Well, I feel like if we drew this right triangle by your theorem, like there's no rational number that's going to fit this the length of this hypotenuse. Ah! Yeah, that's what that kind of thing means.
Then he probably ate some beans. Yeah.
Okay, so if you have a polynomial, if irrational roots exist, it must have this form. It must be plus or minus a factor of the constant term divided by a factor of the leading coefficient. If there's a rational root, it will have that form. If you try all such possibilities and they don't work, then it has no rational root. So there's a theorem. It's not that hard to prove, but we won't prove it. Let's actually put it to use. So a root, remember, is just a number that when you plug into the polynomial, the output is 0. We have from the factor theorem, if you can find such a number, where if you plug into the polynomial, the output is 0, then that guy is going to be a factor, which means you can factor the polynomial where this is going to be one of the guys in parentheses, right? That we're going to put it all together then. So consider this polynomial. Let's look at R3 minus 3r squared plus r plus 5. So consider this equation. I want to be able to solve this equation. This is my polynomial, p of r. I would like to find numbers that when I plug into that, I will get 0. Now, according to the rational roots theorem, if they exist, what I'm going to do is look at the coefficient of the first term. Notice that the factors of that are plus or minus 1. Look at the last term. Notice that the factors of that, well, it's prime, so plus or minus 1 is going to be a factor, plus or minus 5 will be a factor. So pretty much, I want to talk about all the ways I can factor these integers. What are the factors? The integers that can divide into this number. Okay. 1 and 5 are the only ones, plus or minus. So what you can do is look at the numbers, plus or minus. If I take this factor, 1, I would divide it by all the factors of that. Well, there's only 1, comma, plus or minus this factor, 5, divided by every possible factor of that. There's 1, there's 1. So there are 4 candidates for the rational roots of this particular function. It can either be plus or minus 1 or plus or minus 5. Now, I don't know ahead of time whether or not these are going to actually work, but what I would do is I would try them. So I would check. Let's say r equals 1. Plug in r equals 1 here. What you would get is 1 minus 3 plus 1 plus 5. Is that 0?
Yes. No.
That's not 0, so we don't care. We want to the next one. Minus 1. Plug in minus 1. You get minus 1 plus 3 minus 1 plus 5. Minus 3.
Yeah, that's 0.
That actually gets you 0. Now, once you do that, this means 5, r equals 5 is a root of that polynomial. Huh? Negative 1. R equals negative 1 is a root. This means, by the factor theorem, that r minus a negative 1, or in other words, r plus 1, is a factor. What does it mean to be a factor? Well, here's where long division comes in, which I asked you guys to review. You should be able to divide this polynomial by that expression, r plus 1. And you will have 0 remainder, and hence a way to factor this guy. So we're going to write this down.
R squared.
What?
R squared would be the first one. Yeah.
Oh, well, I didn't start it. So let me just point out here. The way you actually set this up is going to be very important. You need to write things in the descending order of powers, r to the 3, r to the 2, r to the 1, r to the 0. You also need to make sure that you leave space for all powers. Meaning, for example, if there was not an r, pretend there wasn't an r, you would literally leave a space for the r. Or if you like, you could put in 0r. It's very important that every power has a space. So even if there are things missing, once you start from the highest power and count all the way down, in descending order, you need to leave space for everybody, so that's very important. So that is how you start, that is the beginning, that is the setup. Now, here's how long division works for polynomials. You're going to take the biggest guy here, you're going to divide into the biggest guy there, right? R divided into r cubed goes r squared. Right, so you take r cubed divided by r, you get r squared. Now what you're going to do is you're going to take the r squared and you're going to multiply everyone here. I'm going to take the r squared times the r cubed, put it underneath. Take the r squared times the 1 plus r squared. What you're going to do is you're going to subtract this line. The r cubed's died.
Minus 4r squared.
Then what you're going to have is minus 3r squared minus r squared is minus 4r squared.
And you bring down the r, right?
And then you repeat the process. We'll bring down the r when it's convenient. R into minus 4r squared goes minus 4r. I take minus 4r, multiply everybody here. This times that, I get minus 4r squared. Minus 4r times 1, I get minus 4r. I'm going to subtract this line, and this r comes down. The minus 4r squares die. I will have plus r minus a minus 4r, which gives me plus 5r. And I repeat the process. R into 5r goes 5. I will take 5, multiply everybody there. So it's the 5 times the r is 5r, plus 5 times the plus 1 is plus 5. These die, this 5 comes down. Now I have plus 5 minus 5, which is 0. Now, it is very important that you get 0. Not, you made a mistake. Or, the other possibility is that r plus 1 is actually not a factor. Which means you made a mistake. Right? So either you messed up here and you shouldn't have gotten 0, or you messed up somewhere right here. Once you do the long division, you have to get 0. If you get a remainder, it means the thing cannot be factored using that. Now, the fact that I got a 0 means the following. Here's what that means. This means when I take r cubed minus 3r squared plus r plus 5, and I divide it by r plus 1, the result is going to be r squared minus 4r plus 5 plus 0 remainder. Right? Technically, you write it as 0 over the r plus 1. But what does that actually mean? Well, I can multiply both sides by r plus 1. And that means I can write this cubic as this expression. Now, this is something I can factor.
Plus 3r minus. No.
Plus 5.
Is that, you have to use the quadratic formula.
Double
Yeah.
one.
So you have to remember. No, r minus 5r plus 1.
R plus 1.
R plus 1, r minus
This should be
You
enough.
get a negative
R
5.
minus 5.
Yeah. Oh yeah, I think it's roots are 2 plus 2 r
Plus
minus
minus
1.
4 minus 5. Minus 5 plus the 1.
Yeah, they need
No,
to
that's
add
the
up.
minus. No.
Well, yeah, none of that is going to work. If I take a plus 5, right? If I do 5 and 1, it has to be 5 and 1. Let me just go through this. So after grading some of the tests, things like this might be necessary. How to check if your factoring actually works out? It turns out that the product of the outer terms, you multiply them. Here you get r. The product of the inner terms, here you get 5r. You need to find a way that you can actually add or subtract these two in order to get the middle term. Now to actually get a minus 4, what would you actually need?
Minus 5 plus 1.
You need a minus 5 and a plus r, right? Which means you would have to have a plus here and a minus here, right? Now when you actually look at that, what's the problem?
Minus 5 times.
You would multiply this out and you get a minus 5, so that's a contradiction. You can't actually factor, right? So if you think it might factor, you try it, you need to know when it's not going to work. So here, this actually doesn't factor further. So, to find the other roots, just use quadratic formula. Which I simply remarked earlier was because like more than half the class made a mistake or just didn't know the quadratic formula at least once on that test. So how would the quadratic formula actually work? So if we have r squared minus 4r plus 5 equals 0, what does the tell me the general formula first.
Minus b
Minus
plus
b
or
plus
minus
r
squared
squared.
divided by 2a.
Okay. First important fact. Not correct. Right? All the way. Okay? That's the first important fact that a lot of people seem to forget. So they didn't divide the b by the 2a. Okay. There were a lot of other issues, but that was the one that showed up quite often. So that goes all the way. Okay. Now the a is the coefficient of the x squared, the r squared. The b is the coefficient of the r, and the c is the constant. So this would be minus b, which is going to be plus 4, plus or minus the square root of b squared, minus 4 times all over 2 times 2. So this is going to be 4 plus or minus. What's under this? That's 16 minus 20, that's minus 4 all over 2. What's that going to be?
2 plus or minus I. 2 plus 2i.
2 plus 2i all over 2. 4 plus 2. So that's 2 plus I, plus or minus. Okay. I erased the original. So, in other words, if I have r cubed minus 3r squared plus r plus 5 equals 0, then this would mean my r is actually either minus 1, or my r is going to be 2 plus or minus. This you'll notice will actually give you 3 roots. Here, your r1 is going to be the 2 plus I, your r2, your r3 is going to be the 2 minus I. Maybe I should actually,
But would you,
yes.
I mean, once you have those complex numbers as roots, do you then move into stating your y as some part?
Well, I didn't actually think of this as a differential equation. So
right.
that could be another step. I just wanted to focus on this so that if there are any questions on the process, you could ask me now. Are there any questions on the process? Because I did actually kind of rush through it because I expected you guys to kind of have seen this before.
No, the quadratic formula.
No, the quadratic formula. I also wanted to make sure that you guys all know the quadratic formula. Maybe I will give you another thing to try. Originally, I had one example here, but let me pull up another one.
So like in higher order differential equations using this process, we would just keep doing the long division.
Yeah, so you would do that rational least theorem thing, try to plug in convenient numbers that will make the polynomial give you 0, and then you divide. And each time when you do the division, the polynomial would break down to one smaller degree. So if it's a cubic, it will break down to a quadratic, and you can factor that. If it was a 4th degree, it will break down to a 3rd degree, and then you can do it again to break it down to a 2nd degree, and so on and so forth. Try this example before I actually move on. Let's see. I'll give you ones with some nice numbers. So let's not even worry about complex roots at the moment. Let's just keep it simple. Just to make sure that everyone's on this. Then maybe I'll actually also talk about some other general tips to do with this. So, solve y triple prime plus 10y double prime plus 29y prime plus 20y equals 0. I'll give you 5 minutes. Hurry up. Make sure you try it so that if you have any issues in executing this, you can ask me right now before we move on. We're going to start doing series solutions yet, so you guys need to review your series.
What?
So if you did Math 203, that's you have to review from Calc 3. If you did Calc 2 pretty much anywhere else, you would have done series. So you might have to go over your Calc 2 stuff. But series is the next topic. solving that. Yes? Okay, what's the answer?
C1 e to the negative 2. C2 e to the negative 4.
C1 e to the
Negative 2. C2 e to the negative 4. C3 e to the negative 5.
Let's check. So, we know that the characteristic equation here is going to be r cubed plus 10r squared plus 29r plus 20 equals 0. Now, first thing you want to do, and this is a general principle, you always want to go with the easiest possible strategy first. So this is a polynomial with 4 terms, so actually the first thing I would think about is something like factor by grouping, but clearly here you should recognize that that doesn't work, because the common term here is the r squared. If you factor that out, you're left with an r plus 10. Common term here is like 1. Factor that out, you're left with 29r plus 20. You don't get the same thing in each pair, so factor by grouping won't work. That's when you start to think of something more complicated. Now you're going to try certain numbers here. What are the numbers you would try? Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. These are all the possible candidates. That's a lot of numbers. You start with the smallest one first. It's kind of easy to see because they're being added everywhere. If you use one of the positive numbers, you're never going to hit 0. So I'm just even going to focus on all the negatives, right? So what I would do is try negative 1. If r equals negative 1, what would I get? I would get minus 1 plus 10 minus 29 plus 20. Does that actually work? That actually gives us 0. Oh, got lucky. So what that means is, if I take r plus 1, it should divide into that polynomial evenly and leave me 0 remainder.
So it's only one that gives you 0?
Huh?
Can there be any cases where like more r's give you 0?
Yeah, it's potentially more. In fact, if that is to be believed, I know there are 3 of these that give you 0.
Oh, okay.
But you do one at a time. Right? So I'm going to go here, r cubed plus 10r squared, make sure all r's are accounted for. This into that goes r squared times that gives me r cubed plus r squared. Subtract the r cubes die, I would have here 9r squared. R into that goes plus 9r. 9r times this, 9r squared plus 9r. Subtract the r squares die. 29 comes down, subtract 9, I get 20r. R into this goes plus 20. 20 times that, 20r. 20 times the 1 plus 20. Subtract this, 20 comes down, 0. That's supposed to happen. What this means then is that my P of r can be written as r plus 1 times r squared plus 9r plus 20. That one actually factors. Factors of 20 can do 5 and 4, and they actually add up to 9. So this means that my r is negative 1, my r is negative 5, or my r is negative 4, which means that's my solution. The homogeneous solution given by C1e to minus 2 plus C2e to minus 5t plus C3e to minus 4t. So that was correct. 3y double plus 3y prime minus 2y equals 0. Okay, what do we try here?
Mix of a of 0, which is plus or minus.
So this means we have 3r squared plus 8, 3r cubed plus 8r squared plus 3r minus 2 equals 0. What would we try here? Of course, factor by grouping you should see doesn't work. Well, why we're jumping in here. That's actually the first thing you should look for. What would you try?
Plus or minus 2 over 3 plus
Plus or minus?
2 over 1.
Well, 1 over 1, try the smallest. Plus or minus 2 over 1. Plus or minus
2 over
1 over 3. Plus or minus 2 over 3. These are all the guys you would actually try. Right? The factors of this are 1 and 3. The factors of that are 1 and 2. So you want all possible combinations where 1 or 2 is on the numerator and 1 or 3 is on the denominator. So you have all these possibilities. You actually have 8 possibilities here. Of course, you start with the smallest ones. Positive 1 doesn't seem like it's going to work, so I would again try negative 1. I would have minus 3 plus 8 minus 3 minus 2. That actually gives me 0. Okay, again, with the r equals minus 1. This means I should be able to divide by r plus 1. 3r cubed plus 8r squared plus 3r minus 2. R into this goes 3r squared, this times that, 3r cubed, this times that, 3r squared. Notice that it's lined up with my 3r squared, it's not all over the place so I don't get confused. So this is going to be 8r minus 3r, that's 5r squared. And r into this goes 5r, 5r times that is 5r squared, plus 5r. Subtract those to each other, the 3 comes down. I would have 3r minus 5r, that gives me minus 2r. R into this goes minus 2, and minus 2 times the r, minus 2 times the 1. That dies, the minus 2 comes down, and again I get 0, which I should get, which means that my p of r is going to be r plus 1 times 3r squared plus 5r minus 2. How does that factor? Does it factor?
Yes.
What is it?
3r.
3r and r, only 2 ways you can get it. And
plus
2.
2.
So you can take 2 and 1. Notice that out here, this gives you 6. Out here, this gives you 1r. Can I use that to get to positive 5r? Sure. Make this a plus, make that a minus. Minus should be here, plus should be there. And that actually works out. So this means my r is either minus 1, or my r is 1/3, or my r is minus 2. Which means my homogeneous solution looks like what?
C1 equals C2 equals negative 1/3.
Hopefully that was enough examples. Let's actually move on to something cooler. We are going to now talk about something called the roots of unity. What does that mean? Let Z be a complex number. Solutions to Z raised to the n equals 1 are called roots of unity. Now, sometimes that is going to be easy to find. If your z is, for example, the real number 1 and your n is 2, is just, if your n is 2, then your z will be plus or minus 1. And that will give us all solutions. And notice for,
1 is a complex number.
yes, it is, with imaginary part 0. I want you to notice that complex polynomials have n roots up to multiplicity, which means you should be expecting to find n factors here, where factors can be repeated. Now, in general, that can be kind of difficult. We know that if we had to solve something like x squared equals 1, that's no problem. Or if I had to solve x to the 4th equals 1, you already start to see a problem. X cubed equals 1. You can actually deal with that. That was on the actual exam. But once you start getting to things like x to the 9th equals 1, or x to the 10th equals 1, or x to the 6th equals 1, then things start to get a little bit sketchy.
Is x to the 9th just x cubed then? So like, you can still get a cubic, you find roots using the cubic?
Yes. Yes, you always try to go with the most basic thing that can work. So even like, for example, if you had to solve z to the 6 equals 1, technically you could bring that over, and you could think of this as, we can think of this in either as cubed squared. You could also think of it as a squared cubed, and use either the difference of squares formula here or the difference of cubes formula here. By the way, this goes in line with what I mentioned earlier about the general principle. You always want to apply the easiest one first. It turns out that if you were to go with this one first, it will actually be a lot harder. You want to go with the way where you apply the difference of squares first, and then you apply the difference of cubes after when necessary. So there are times when you can get around it, but in general, it's going to be sketchy if you can't actually write it as something where you already have some special formulas that cover those cases. So the idea here is the following. A general way to solve this, where you don't need to remember any of those algebraic formulas, even though you should, it's not an excuse for you not to remember the difference of squares and the difference of cubes. Is to use the polar form of a complex number. What is the polar form of a complex number? Z is said to be a polar form. If Z is written as R e to the I theta. Turns out that every single complex number in the complex plane can be written in that form. How do you actually think of being written in that form? Well, if your Z equals A plus IB, what that basically means is that you can imagine this as some point in the complex plane, where if I look at I as the y-axis, so the y-coordinate is always attached to it, an I, and this as the real axis, there's going to be some point here, A comma B, that corresponds to that complex number. What you can then do is realize that I can measure an angle, positive angle with the positive real axis, and I can call that length R. You'll notice that this height here will be B, this length here will be A. And what you'd be able to write B as trigonometry. It's written as R.
Sine of theta.
This is R
R times the sine of theta.
Sine.
Ri.
sine theta. This A will be R cosine theta. Right? X is R cosine, Y is R sine. Now, what does that actually mean?
Doesn't our sine take on an I?
Yes, typically there's an I here. That goes with the complex part. So what does that mean when you actually write it in this form? This means that your Z, which is equal to A plus IB, I actually didn't need the I attached there because it's going to come here. The A is going to be given by R sine theta. The B is going to be given by R sine theta. What you'll notice is that R will be a common term. We'll factor that out. And what is that guy? That's e to the I theta, according to Euler's identity. So I can write any complex number in that form, which makes it very convenient. In particular, there are a few that are very conveniently written that you should know in particular. I can write the number 1 as a polar form. In fact, this is going to be 1 e to the... try to write it in this way. It's pi over 2. Now, notice here what, it's not pi over 2, it's actually going to be, 1 would be the point here, right? That's just the real number 1. Okay, what's the angle?
0.
Well, it's 0, but we can be an angle, which means there are actually an infinite number of them that will work, right? It means every time I add a 2n pi, this is still a solution. So it means that I can think of 1 as e to the 2n pi for all n. We'll see how this actually fits together pretty soon. I can also think of the number -1 in a similar fashion. -1.
Why can't they just be real? Why is that like... Oh, for one, I'm sorry.
This is theta, yeah, it's all the ways I can go around. Okay, what about -1? Well, this means I'm at this position here. What is that angle? Well, that's going to be pi. So that's, and there's an I here, by the way. That's going to be e to the I pi. But again, every time I add a 2n pi, I get the same thing, which means I can actually write this as e to the I 2n plus 1 pi. N is an integer. I can do the same thing for the imaginary number unit. If I have I can also write that as e to the I some angle. What angle? Well, I will be the point that's right here. The angle here is going to be pi over 2. So that means I start at pi over 2 plus 2n pi. And minus I, which means I have this guy down here, -1 unit. I can look at this as 3 pi over 2 plus 2n pi. So I can think of the basic building blocks of a complex number. The unit 1, the unit -1, the unit I, the unit minus I. And I can actually construct any complex number using these. Let's actually see this in workout in action. Now I'm going to use it on something that we already know how to do, so you can see that it actually works out. Example. Find all the roots of R cubed equals 1. So yes, you could bring this to one side, think of it as a difference of cubes and use that formula, and then use a quadratic formula to find the roots of the quadratic part. But let's actually use this way. So here, or let's make this z because I'm doing one the right part. So here what I would do is I would set z equals to r e to the I theta. This means that my z cubed is going to be, come again?
E to the 2n pi.
Well, what is 1?
2n pi.
So this means that z cubed is equal to I to the 2n pi. There. Alright, using the, I wrote it right there. Now, here's what we can actually do.
Wouldn't
We
I
can, what?
Wouldn't I be 0 because it's on the real plane? E be 0.
Why would I be 0?
Because it only has a real component. It doesn't have an imaginary component. It's on the real.
It has imaginary components. Z is assumed to be a complex number.
I mean, e to the I 2n pi. That would still work. Because on top you wrote 1 is equal to e to the 2n pi.
Yes, but that's Z cubed.
Oh.
So now, what's going to happen if you want to solve for Z? Take the cube root of both sides. So you're going to get Z is equal to e to the I 2n pi over 3. Now what you're going to realize is this is going to loop itself. And of course, you're dividing 2 pi into 3 parts. So once you actually get 3 solutions from this, the solutions are going to start to repeat. So what you can do then is know that this will give you all roots for n equals 0, 1, 2. In fact, in general, that's how you're going to do it. Once you do something like this, you're going to set n go from 0 all the way up to 1 less to, what do I want to call this? Call it r minus 1, where r is a degree. And so now, you see that I do all of those guys, I will just get all the roots. So, if my n equals 0,
Isn't 1 always going to be a root
4,
for something like this? Because
yes,
because you're starting in
because you're starting with n equals 0. So if n equals 0 and I plug it in there, what do I get? Well, I would get z equals e to the 0, which is 1. There's my real root. If n equals 1, I would get my z is equal to e to the I of 2 pi over 3. What is that?
cosine pi over 3 plus sine.
It's cosine of 2 pi over 3.
I don't remember, man.
Shout it all at once. Huh?
Sine of 2 pi over 3. Cosine?
One minus radical.
What's cosine of 2 pi over 3?
Cosine of 2 pi over 3.
It's radical 3 over 2.
Uh-huh.
It's minus a half.
Oh.
Sine of 2 pi over 3.
That's rad 3 over 2.
That's rad 3 over 2. By the way, you can know that complex, there's a little shortcut you can have so you don't have to burn your brains out. Complex roots always come in conjugate pairs. So if you have an A plus an IB, the next root, there must also be a root of A minus IB. So I didn't have to calculate this, didn't need to calculate. Since complex roots come in conjugate pairs. I.e., if A plus IB is a root, then so is A minus IB, and vice versa, of course.
So how do you know that it's at 2 though?
Come again?
How do you know that it's root n equals 2 though?
That was the only other option. I was doing n 0, 1, and 2.
Why does this property exist for complex roots?
It's kind of in the quadratic.
Yeah, because the I comes from a square root of minus 1, which gives you a plus or minus. So you'll always have it show up in pairs. There'll always be a plus or minus attached to the radical part. So that will give me all three solutions. And I'm pretty sure we actually did this one already. What you can remember to compare. If you had r cubed equals 1, what you could have done is r cubed minus 1 equals 0. Then you will remember the difference of the cube's formula. And so you get r equals 1. From here, this one's not going to factor. You do the quadratic formula. R equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. So this is going to be minus 1 plus or minus, that's actually a radical 3i all over 2. You get the minus 1/2 plus or minus radical 3 over 2i. You get the same value. But in this way, you can generate all the roots by just looking at the exponential and plugging in all the ends going around the circle. It turns out that for this guy, you will have roots at this point. If you think of this as a circle of radius 1, you would have roots at this point. You'll also have roots at 2 pi over 3, and you'd have roots at 5 pi over 3. There's going to be like this 3-pronged thing that gives you all the roots around the circle, and it splits up depending on what your n values are.
Does that mean this only works for odd degree polynomials? Because
No, it works always.
But if you have complex odd degree polynomials with complex roots, because if there's always a pair, your zero, whatever your zero value is going to equal 1, and then your 1 and 2 value or some other pair of values are going to equal 2 complex numbers. So that has to always be odd.
I'm not sure what you mean.
So we
you
have-
want it? Let's try an even one.
Then
How
you're
about
going
trying-
to have something that's non-complex roots, or at least
We're going to have two
well,
pairs.
you can have both. It can be a combination.
Yeah, you can have a complex root. There's nothing against that. I just know once you have one of the complex variations, you would have the convex variation. But I'm not saying they're only going to be complex roots. You can have a mixture of real and complex roots.
Is it always going to be the next n value, or it could be random?
It could be random. It doesn't have to be the very next one. So let's actually try another one. So, in fact, let's actually jump into solving an example with this one. Let's look at y to the 6th prime plus y equals 0. Before that, but let's actually look at this one. So, we would say here, the characteristic polynomial is going to be r to the 6th plus 1 equals 0. This means that r to the 6th equals minus 1. Now, yes, I could think of that as r squared cubed and think of it as the sum of cubes formula, but we're doing another way. Now, minus 1, another way to write that is to do what? E to the I.
1, 2, 2n plus 1 pi.
2n plus 1 pi. So it's e to the I pi, remember that's equal to minus 1 because of that equation. You're going to kill me, I talk about it. That equation, the most beautiful equation ever. How dare you solve that equation? Okay, that's going to be pi plus 2n pi, or 2n plus 1 pi, because I know e to the I pi gives me negative 1. And what I would do here is I would say n goes from 0, 1, 2, 3, 4, and 5. Once I start to go to 6, that will start to repeat itself. This means that my r is going to be, I would just divide both sides by 6. E to the I, divide both each power on each side by 6. To the 2n plus 1 pi over 6. Now once I run through all of these, I will generate all 6 roots. So, start at the beginning. Start with n equals 0. If your n equals 0, your r is going to give you e to the I pi over 6. This is going to be sine of pi over 6, cosine of pi over 6, plus I sine of pi over 6. Cosine of pi over 6 is radical 3 over 2. Sine of pi over 6 is 1/2. Then you go on to n equals 1. This means r is equal to I to the, plug in 1 here. So that will be 3 pi over 6, which in other words is pi over 2. This is going to be cosine of pi over 2 plus I sine of pi over 2. That's what we want. Cosine of pi over 2 is 0, sine of pi over 2 is 1, so that's I. If I look at n equals 2, this means that r is equal to e to the I, plug in 2 here, that would be 5 pi over 6, 5 pi over 6, that is cosine of 5 pi over 6, plus I sine of 5 pi over 6, cosine of 5 pi over 6 is minus radical 3 over 2, I sine of 5 pi over 6 is still 1/2. Now what you will notice is I am missing 3 roots.
You have
This
2
is
plus.
alternate sums.
But you also notice that I have 3 different complex numbers where none of their conjugates are showing up. Right?
Yeah.
So notice that I went in order, but I didn't actually repeat the complex numbers, which means automatically another root is going to be the radical 3 minus 1/2. Automatically there should be a minus I as a solution, and automatically there should be a minus radical 3 over 2 minus I over 2.
It doesn't matter if you know which one is.
So that is, it doesn't matter what n value they show up. The n is just helping me to figure out what all the numbers that I have to cycle through. But ultimately, if I were to continue this process, those are the guys that would have popped up. And so, finally, what this means is the following. R is either equal to plus or minus I. That's the first 2 roots. The second and third roots is going to be radical 3 over 2 plus or minus I over 2. The third and
5th and 6th.
come again? This should be third and fourth, and this is the 5th and 6th. This is going to be now
Negative radical 3 over 2.
negative radical 3 over 2 plus or minus I over 2. Those are all 6 roots. What does it say about my homogeneous solution?
Very long.
Huh?
Very long.
It's very long, that's one thing it says. The other thing it says is
Cosine t
C1 cosine t
plus c
plus C2 sine t plus C3
e to the radical
e to the radical 3 over 2t cosine t over 2 plus C4 e to the radical 3 over 2t sine of t over 2 plus c5 e to the minus radical 3 over 2t cosine t over 2 plus c6 e to the minus radical 3 over 2t sine t over 2 good times.
There you go.
So there you go. It's a sixth order differential equation, which means it definitely has 6 linearly independent solutions, namely these guys.
That also be a
Huh?
infinitely split unit circle, it's parts, about 36 lines along the unit
Yes.
circle, which are all.
So on the unit circle, you would have like 1, 2.
You don't
Where-
need, you
no.
don't have pi over 2, do you?
So the angles were pi over 6 was one. I think 5 pi over 6 is another one. We also had pi over 2 and right. So the complex numbers would be located here, 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 and here. Notice that none of them are on the real line because there's no real solution. So yeah, plus and minus I is the solution. This one is radical 3 over 2 plus 1 over 2i. This one is radical 3 over 2 minus 1 over 2i. This is minus radical 3 over 2 plus 1 over 2i. This is minus radical 3 over 2 minus 1 over 2.
So we would need 2 reals to draw a fully sliced pizza.
Yes. To get these here. We need 2 more reals, which I could get by just multiplying that through by r to r squared.
Yeah.
So r to the 8th minus r plus r squared would actually give you those other 2. I mean, I have more examples, but I'm kind of out of it today, so I will leave you guys to finish up some examples. A y triple prime plus 5 y equals 0. Y to the 4th plus y equals 0. C. Y triple prime plus y equals t plus e to the minus t. Try those for the next time. No quiz on Wednesday. So we're going to finish this up.
No problem.
I've already sort of slowed down on this, so probably not going to have a quiz for the next 2 weeks or so. But next time we'll finish that up and we will actually look at series. So in the meantime, review your power series, make sure you remember how series work. I will hand out the exams right now.
Trust the first test that's on.
I don't